All right, so next questions we're going to be studying is 31. This is the linear algebra section 1.4. Yeah, so I sort of started ahead, but this is 31a. To prove it to me that a plus b times a minus b cannot equal to a squared minus b squared. First of all, we should know that because we should have studied the theorems in our section and sufficiently enough so that, you know, there's no such thing like that exists. But nonetheless, they ask us to test it. So I think the only key point about this question is make sure, you know, you don't overcomplicate things, right? So when you choose A, B, and C, you probably notice on the solutions that, you know, they choose relatively simple numbers, right? And that's the whole point, because if you don't, I mean, you're still going to be able to prove it, but then you have to go through a lot of multiplications. Zeros are beautiful in multiplications because it doesn't matter what you're multiplying. If you times it by 0, it's 0. So that's why. So stick with some simple matrices, right? I mean, almost close to identity matrices if you need an inspiration, right? So A, I put 1, 0, 0, 0. But again, that's the whole point, right? I didn't want to do completely all the way zeros just in case, you know, maybe there's too many zeros, so they'll cancel a lot of things out and they will coincidentally be same, right? So just make sure you put some variety, right? Just to make sure that there's no fluke, right? But, you know, for most cases, you know, they don't equal in real situations anyway. So, you know, unless you get really, really unlucky, I highly doubt you're going to have trouble with this. And even if you get unlucky, just, you know, randomly switch the matrix values, entry values, and you'll be fine. So, but anyway, so that's nothing groundbreaking, right? So I just added a b and a c, and then I come up with this, and then I did a squared and b squared. Whenever you do a squared and b squared, it just means a times a, right? That is also true in the matrix algebra. So I just, you know, because I can't do it on top of my head, right? If it was like, if a was an entry, then I could do it, but you know, so because of that, I actually wrote down like this, did the multiplication, and then subtract them together, and obviously this and this do not equal in a wrong, located in a wrong position, right? So that's all it is. Easy stuff, right? No big deal. The part where it gets a little more interesting is B. Say the value formula for multiplying out a plus and AB. Value formula. Okay, so let's take a look. So it's going to be B. A plus B, A minus B. So, now, it's not that it's hard, but maybe you're stuck as to, well, where did you get this new formulas from solution manual, right? If you're one of those people who are stuck. It's really simple. So I'm just going to say, let A and B, now you could choose this or this, it really doesn't matter, okay? So what I'm going to say is, I'm going to choose this one, right? For example, then I'm going to say, let A and B equals to C. Why not, right? If A and B are allowed to be added, then, you know, there shouldn't be that many restrictions, right? So if that's the case, then it's going to be C, A minus B, right? On the theorem, which is found in the very first, was theorem 1.4.1, right? Which letter is it specifically? It is, oh yeah, literally copy and paste from F. Theorem 1.4.1 F, which says A times B minus C is AB minus AC, right? So that's on page 39, by the way. So if I have that, it says what I'm doing here is correct. It's going to be C, yeah, right letter, CA. Equals to CB, right? So I'm trying to relate back to this though, right? So let's now expand to C. So what was C? C was this, right? So let's just, you know, plug it in again. So it's going to be A, B, which replaces C because C equals A plus B, right? So A minus C, again, is A plus B, B, right? Same thing as this, right? And then now, yeah, and that's all there is. So, because this, I was just trying to see how this will link to C, to 31C, but nonetheless, so that's the value formula that will work, right? Now you can put A in the back or the front, really. Oh, no, yeah. Oh, actually, that, we're going to talk about that. So for some people who might be saying, well, let's just put A and B in the front because, you know, that's more aesthetically pleasing, right? Be careful. Remember, in multiplication for linear algebra, order matters, right? But there are times when order don't matter, which brings us to C. I think I can make the rule. Yeah. So C. What condition can you impose on A and B that will allow you to allow 31A to happen, right? So what is 30? So remember, A plus B times A minus B cannot equal to A squared minus B squared, right? So when can we make this happen, right? Because you know. So how do we make that happen? Well, this sort of, and that relates to what I just said in B. But yeah. No spoiler. Let's keep going. So, how do we make that happen? So let's just expand. So just do what we did right here, right? Actually, we could do that, right? Because A, B, is that? Oh, it looks blue from here. Ah, well. Anyways, A plus B, A minus B. Oh, the oil thing is just, you know, because if you look from the down, the light glares back, so the color changes. I don't know what I'm talking about these things. I'm kidding. I have way too much time on my hands when I do stuff like this. Anyways, so that's that. So that's going to equal to A squared minus B squared. Okay, so let's say it can happen. Let's find the algebraic expression so that we know exactly when it's supposed to happen, right? So A plus B, A minus B, that's what we just did here, right? I'm just going to copy and paste it here, right? So A plus B, A minus A plus B, B equals A squared minus B squared. Okay, so if that was a case, oh wait, for B, okay, I haven't checked the solution yet, or maybe I'll do that right now. You could be doing that as well, but let's see, 32, 31. Oh, okay. All right. Fair enough. Okay. So, yeah. So what I was looking at was where did my sheet go? I have it somewhere. Oh yeah. Yeah. Sorry. Yeah. So what I was saying though is that. Yeah, so we came up with, for B, back to B again, so we had this, and basically they wanted to expand this further. I don't really know why, but I guess. So since order matters, we look for theorem 1.4.1 E this time, right? Because the A is at the back. So that's going to be the same thing as AA plus BA minus A B and BC. Okay, so yeah, so that's that. And that's going to be A times A is A squared plus BA, and then, oh no, why did I put BC? Not that. It's going to be BB, A, B, B, B. Oh yeah, that's why it's not BB. I'm going to simplify that B to B squared. Okay, so this is where it comes in. Okay, my bad. I was going to do that in C, but yeah, I mean, you could do it in B and then just, it doesn't matter. I want this for C. And I'll tell you why. A squared plus BA minus AB minus B squared equals A squared minus B squared. Okay, so here's an interesting thing. So A squared right here, B squared right there. Okay, so interesting. See this? So you're adding something, right? So this value and this value is exactly the same expression, which means the only thing that's getting in the way, the baggage that prevents this equal from being equal, is this, BN and AB. So if I can somehow magically make that into 1, or no, not even 1, to 0, right? It has to be 0, because then it's still plus 1, right? Yeah, it's not canceling things up. So if that becomes 0, A squared minus b squared equal to a squared b squared. Assuming BA minus AB. When can, so A equals to 0. Now, when could this ever happen? And this is where we were, this is where commutable term comes into play again, right? So what's, because remember BA equals AB, or whichever order. Order doesn't matter when you do multiplication, so that's why A and B are, A, B, and B, sorry, let me say this again. A and B are commutable, right? So, if they are commutable, that equals that, right? So then BA minus AB, which is the same thing as BA minus BA, because they're commutable, so order doesn't matter, right? That will become 0. So, that operation, that expression that we've been, mathematical expression we've been working on back in A, it would work when A and B are commutable. Anyways, that was, yeah. See, I like questions like this. It gives you some big picture as to how mathematics actually work. And these are and this is where we get to apply it on our software or whatever, other applications. But nonetheless, okay, so that is 31. 39 is, what are you, 39? Yep, it's on the next page. Yeah, so that's going to, so, actually, I'm going to just, yeah. Alright, so we're going to be looking at 39. Yeah, so I actually sorted it ahead again because I lost the power for that video. So, but anyway, so you have no, 39. So it's already on a solution that should be pretty straightforward, but just going through things. So the only thing you have to worry about is when you inverse a multiple matrices like A, B, right? Make sure B and A are flipped on the byproduct. So just make sure you don't forget doing that, right? And after you do the flipping, the inverse applies to everything inside, right? So for example, AB to the power of -1, that's going to be B to the power of -1, A to the power of -1. So A and B flipped, and then put inverse to each players, right? So that's what it is. So if A and C to the power of -1, they haven't been touched at all because there's no inverse, so it just stays the way it is, right? Nothing has changed. Here there is an inverse, so we're going to do the inverse and C inverse other way around. But at the same time, you put inverse for both of them anyway, right? I know each of them already has an inverse, but the rule still applies the same, right? Try to explain that to your debt collectors. Like, you can't put more debts on me. I already have a debt. Yeah, that kind of logic doesn't work in mathematics, unfortunately. D minus 1. On this, you can multiply. You have a power to multiply things by 0. But I'm getting off topic. So d to the power of -1 stays the same because nothing is being done to it. And so the only thing you need to worry about is that you have to really understand the definition of inverse. So it's a pretty common sense, but just in case, right? So if you have a principal, which is investment term, okay. So if you have an original number, whatever, and if you times it by the inverse, it will always give you 1. That is a definition, right? It's not 1 over something. That could work in certain situations, not in matrices, right? Because you can't do 1 over a matrix, right? But nonetheless, that's what it means, right? Original number times with something inverse, right? Which could be 1 over something, but there's no guarantee. Only thing is, if you do number times its inverse, then it will give you 1. It has to. That is the definition, right? So if that's the case, then you have the A and A. You have the A and A to the power of -1, right? So you have this, right? So because of that, these inverse and the original number, remember that gives you 1. Or in this case, identity, whichever works for you, right? Yeah, identity is a better way because technic is a matrix, so it's not just 0. It's 1, but then where do the 1s go, right? In a very specific entry. So using the term identity is just easier. I mean, we both know what it means, but that's technicality in linear algebra, I suppose. So now C to the -1, C. So there was an inverse and original number, so that's going to give you identity, and then that's also going to Yeah, and that's also going to give you identity. Identity times identity. It's like times in 1 times 1 times 1. Who cares, right? So they are just going to be b to the power of 1. That's all that is. So, and that's where some solutions. 40, you may, so skip it if you'd like, because I think our prof discussed this. But for people who may have not quite caught it, again, it's a pretty similar idea. AC, AD. So again, since this idea is simple, I'm just going to solve the question. Not touched. This one will count. Okay. The only thing I would worry about, which may or may not happen, is that, are you kidding me? Oh. That sucks. Oh, it goes down. I thought it was okay. Okay. Raise it up. And there goes my shit. There goes my stuff. Okay, all right. So anyway, again, yeah, the only thing I would worry about is, let's say, here I guess the situation's okay because it does that nicely. Oh, like let's say, okay, B, A, B, and C. For example, right? Then you see this expression that says, oh, wait a minute, B and inverse B. I can times them together and make it equal to identity. Therefore, simplifying the equation. Then all I have to do is A to the power of 3 and C. Can I do that? You cannot. You have to be very careful because order matters, right? So unless this two happens to be right next to each other, that may not always work. So just be careful about that, okay? So, but for this situation, I don't think it really matters. But that's what I would totally do for the test questions. But yeah. So inverse of inverse, that cancels out. Inverse of inverse, that cancels out. This two cancel, this two cancel, this two cancel. See, I don't know if you have to write the identity. Maybe you should, just to show that, it didn't just magically disappear, right? So that's going to be C, that. So yeah, and that's what, So pretty simple stuff. So hopefully you follow through. But yeah, just be careful. The order is important, right? So as where is it? So now we talked about 40. We talked about 43. Ooh, okay. 43. Show that if A is invertible, AB and AC. Oh, this is the one with it. Okay. So A, B, and A, C, then B equals C. Okay, so show that if A is invertible and AB is a C, then B equals C. Well, okay. Well, let's figure it out. What can we do about it? Okay, we can do this. So so keyword is if A is invertible, right? So if it is invertible, then I could do this. And then I could say, well, times A on both sides. A inverse on both sides. Since order matters, I'm going to make sure it's multiplied by the same order. Okay, so if that's the case, these two, oh, no, not AB, what am I doing? AC. So, because of inverse times the original function, identity matrix, and well, yeah, so that's essentially just B, C, because identity matrix, yeah. But B equals C. So yeah, that works if A is inversible. But that's a big if, right? Not all matrices can undergo inverse. Oh, that actually, let's talk about that. So when can matrix not be inverse? It's like, well, can't we just inverse anything? Every time when we talk about inverse, the big no-no number is 0, right? So, but wait a minute, like matrix can't have inverse whatever, right? It can't because of the determinant. So remember A, D minus B, C, A, B, no, switch. A, D, A, B, no, B, C stays the same, but yeah. Yeah, so remember that. So yeah, well, no matter what, here in the matrix, you're just juggling with where the entries go. So we don't really risk the paradox of defining anything by 0. Here, however, we do, because it's 1 over AD minus BC. So this is a determinant, right? So if the determinant is 0 somehow, which could happen, right? Then you have 1 over 0. Then this doesn't work, right? No, right? If determinant or a d minus bc equals 0. So that's the idea, right? So if that was the same situation for A, this can't work because we can't find an inverse. That's the idea, right? Now that is, okay, so that is that. And for B, explain why part A and example 3 do not contradict each other. So example 3. So let's talk about why example 3 doesn't offer contradiction. I have a feeling it does, but we'll figure it out. Okay, so A, B, and C. Okay, so same idea. So okay, example 3 is on page 42. But in case if you don't have the book, I'll just write it. It doesn't take too long time. This will be posted late anyway because of that streaming issue. Ah man, I really gotta fix that situation soon. But anyways, so we leave you to confirm the A, B, C equals, okay. So why it doesn't so we have a similar idea. So A, B, and A, C, which happens to be 2, 3, 4, 6, 8. Okay. Now, let's see why this doesn't contradict. Okay. Why would we say that? Oh, because, okay, so I suspect that maybe they're saying why doesn't it contradict is because A is not invertible. Maybe. Because it's exactly the same situation, right? So, yeah, let's give it a shot. So, A, inverse of A is 1 over, no minus sign, not D. So it's going to be AD 0 minus 0. Oh, I see. And that's going to change, right? So that's going to be 8, 3, negative 6, negative 4. So yeah, so it shouldn't work because we have no inverse, 1 over 0, 0. So that's exactly what I was saying. But apparently it still works. I haven't read the whole example, but it works somehow. So what is going on, right? Okay, so this, again, park off again, but anyways, so this is the last question, 43B. Explain why it doesn't work, explain why it doesn't contradict. So I think is a way to come up with a very systematic solution because we know how multiplication is being done, right? So maybe there's a more elegant equation where it would say, well, it's this plus this, so then technically, as an example, right? Let's say these were the entries, A, B, C, D, A, B, C, D. So then technically what you're doing is A times A, and then B times B, and add together, and then you get the idea, right? So if you see these systems, maybe some of them will cancel out just right so that you have a net equation that shows you that, oh, in certain situations, there will be always exceptions, or maybe they're more sophisticated rule. But nonetheless, that's way above our pay grade at the moment. Later on, who knows, right? So, but here all we're trying to figure out is how come it doesn't contradict in this case, right? So all I did was the example, by the way, example 3 is on page, it's on page 42, failure of the cancellation law, right? So, yeah, so they give you A and B and C, and they ask, well, what is A B equals AC. And the moral lesson that they're trying to teach before we're solving 43 is just simply saying you can't, just because it's AB equals AC doesn't mean you can cancel out the A, right? You can, but that's where we have to use the inverse, right? Inverse, so inverse of A, so remember what we did? We did that, and then it canceled out, right? It canceled out both A's together. But in this situation, we can't do that. Simply because A is not inversible. What do I mean by that? Well, let's see. 0, 1, 0, 2, that's the A, right? So if I want to make it inverse, that's going to be determinant. AD 0 minus 0, right? So I don't even have to bother with, no. It's like Sheldon. I have to complete this somehow. That's weird. But anyways, but it doesn't matter what I have here. 1 over 0 can't be done, right? So you can't have an inverse. So in this situation, we can't really prove that B equals to C. It's just that what they're trying to emphasize is that in some happy coincidences, so if it's a fluke or whatever, sometimes we still manage to get the same thing anyway, right? So AB does equal to AC in this specific case, as shown in my calculations. But basically what they're trying to teach you is don't get surprised if you get a lucky coincidence and have the same thing. It doesn't mean you disprove their laws. It's just they're depending on how the interest is specifically positioned and what is being multiplied. I mean, you could technically get some fluke from time to time. Statistically, that sounds unlikely, especially on exams. But if that's I guess they're just trying to. I think they're trying a little too hard to convince you. But anyways, that covers 1.4. That went a lot faster than 1.2. So hopefully that it means it's getting easier. But yeah, that's all that. I'm looking at elementary unit in 1.5. So I should be posting that soon, but we'll see how that goes. Anyways, thanks for watching. Oh yeah, and that's so. Our exam is on Tuesday, covers from 1.1 to 1.4. So at least I have all the contents ready before the exam. It's not a really difficult quiz, so I highly doubt anyone's gonna really bother. And my videos ended up being longer than I thought. But hopefully, now that I uploaded it, it will stay forever. It could be used for, let's say you want to do some reviewing for the next quiz or next exam or final exam, and maybe next year students could be using this as well. So that was the whole point. And please let me know if there's something better I could do. My organization is not my forte, so hopefully I'll be working on that. And I will really try hard to upload things a little faster. It's quite complicated. So yeah, I might actually make a video about that. No, okay. Anyways, that was 1.3. Sorry, 1.4. I will see you again for 1.5 soon. Hopefully.